I'm going to review the types of data or introduce 4 types of data. There are different ways to classify data. I'm going to use this, and this is going to be a basis on which you're going to decide what methods to use. The first step in analyzing data, and one of the things that I find really distinguishes between people who are very accustomed to analyzing data and people who are not. If you're someone who's very accustomed to analyzing data, the very first thing you want to know is what type of data do you have. And when I'm talking to another data analyst, we get through that very quickly. They'll say, you know, the dependent variable is this type, we have predictors of these types, and then immediately I have some reasonable base level understanding of the data set. So here they are, nominal, ordinal, discrete, and continuous, and I'll talk about each of those. First, nominal data, which includes binary or dichotomous, and also includes categorical data. So binary dichotomous, that just means that there are 2 possible levels, male, female, alive, dead, just things where your questionnaire or something about it means that you're only allowing for 2 levels. Now, notice I put a 0 and a 1 here. This is what happens in software when you're analyzing nominal data. It will recode them as numbers, but the reason we call it nominal data is because those numbers aren't real. They're a convenience used by software, but these are only sort of nominally numbers. They're really words, they're states of being. They're not numbers that you could use mathematics on, things that would make sense to add, subtract, do that sort of thing. And categorical is just nominal data that has more than 2 levels, such as blood types. So A, B, AB, or O could be recoded as 0, 0, 1, 2, 3, 4, even though those numbers wouldn't mean anything. There's no natural ordering of nominal or categorical data. And they're only nominally numbers. So ordinal data is almost like nominal data, except that there is an order to the data. They're still not really numbers. So as an example, this Karnofsky performance scale that rates how mobile a patient at a hospital is, from fully active to less active, less mobile, to completely non-mobile or disabled. These have a ranking from the most active to the least active, but they're not really numbers. Again, they're nominally numbers, but they're ordered. So the order is important, but the magnitude is not. It makes no difference. The difference between 0 and 2 here is not the same as the difference between 2 and 4. So the subtraction doesn't make any sense, multiplication doesn't make any sense, only the order matters. As an example of that, another type of ordinal data would be people's rank in a running race. So you might have your first and second place finishers that are in a photo finish almost the same, and then your third runner is way, way back. So the difference between 1 and 2 is not the same as the difference between 2 and 3, but the order is there. And that would be an example of rank data if you're talking about the rank in a race, and it's one important type of ordinal data. This is not rank data. Order and finishing a race would be rank data. The top 5 causes of death in the United States. These are numbers, total numbers, and they're ranked here. So heart disease is the #1 killer, or it was in 2010. at least, and I think it still is. Number 2 being cancer, still very close. And then number 3, way back, chronic lower respiratory disease behind heart disease and cancer. Okay. Now, discrete data is the first type of actual numeric data. These really are numbers. And what distinguishes them is that they are integer data or count data. So back in this leading causes of death, the numbers here, because they're counts, are discrete data. Now, I'm not going to belabor the differences between discrete and continuous data generally, especially in a case like this where the numbers are large. It really doesn't make any difference in this case whether it's discrete or continuous when you're talking about hundreds of thousands. If you're talking about, you know, fewer than 10, then it might make a difference whether you're whether it's continuous or discrete. But in general, discrete just means that only certain values are possible, like the number of people who died of heart disease. And I only show this because here it is shown as a number per 100,000. So these are adjusted death rates. It's still a discrete variable, even though in general this could be decimal. But to me, at that point, it's kind of splitting hairs whether it is discrete or continuous. The important thing is that it's a number and the rules of arithmetic apply to it. So yeah, these are standardized per 100,000. And I only point out here that there are fluctuations in these 4 and 5 positions to give that as an example of likely uncertainty and random fluctuation in the number of deaths due to these diseases. So we have stroke, lower respiratory disease, and diabetes all taking place or taking turns in those 4th and 5th positions. So if you were to think of 1 year as being a sample of all of the victims of these diseases over a large amount of time being the population, then you would have sampling variation from year to year, just due to the people who happened to be around that year and to random events. So, and again, discreteness becomes really unimportant when you have a lot of possible values, like thousands of deaths. Finally, continuous data. So, continuous data are things that have decimals and any value is possible. So, time, weight, length, mass, and you can rightfully point out that you know, maybe time is measured in seconds or hundreds of seconds, and your timepiece only takes discrete measurements. You're right. That's where this distinction between continuous and discrete variables gets a little bit fuzzy. But these are kind of the classic continuous variables, because at least in theory they could be any value. And they may be bounded. For example, mass is always greater than 0, length is always greater than 0, or they may be unbounded, some things between minus infinity and infinity. So with these, both the magnitude of it matters and arithmetic applies. You can add, subtract, multiply, divide, and do